We are looking at section 16.2 today, Introduction to Logarithms. First part says write the equivalent exponential and logarithmic expressions. So we're going to find the inverse of y equals b to the x. This is so I can kind of define what a log is to you. So first of all, remembering from last week, to find an inverse, you'd start by writing y instead of f of x. Well, we don't even have f of x, so we're good there. Then we switch the x and the y. So I've got x equals b to the y, which what that means is that in order to solve for y, we're going to have some other kind of operation. So all I really know here is that y equals the power of b that produces x. So in order to solve for y in this one, we're going to have to use a logarithm. Here's our definition. If x is greater than 0 and p is a positive constant not equal to 1, then y is log base b of x is equivalent to b to the y is equal to x. So first thing we kind of need to get under our, figure out how to do is write the exponential expression in logarithmic form. So here we have 4 to the 5th is equal to, well, that's a typo. 4 to the 5th is equal to 1,024. Okay, so in order to write that in exponential form, to write that in logarithmic form, what we're going to do is I'm going to say that my 4 there is the b, the 5 is y, and the x is the 1,024. So now just looking at our definition, y is equal to log base b of x. So I write down log base b is 4, x is 1,024 equals 5. Okay, so log base 4 of 1,024 is 5. So let's just kind of see what's happened here. If you'll notice, the base of our exponent became the base of the log. So the 4 there is now the base of our log. So I kind of just moved that down. Then the 5 has jumped across the equal sign, and it's no longer an exponent. It's now just on the base level. And the 1,024 jumped across as well, which made it as part of our log there. So what we were finding was log base 4 of 1,024 is equal to 5. Okay, I'm going to do another one. I've got 3 to the negative 4 is equal to 1 over 81. So probably the first thing I would do on this one is rewrite that fraction as 81 to the negative 1 power. You know what? No, I wouldn't. We don't even have to do that. We're wanting to write this in log form. So what I would do is say log, and our b this time is the base of our exponent, so it becomes the base of our log, so that's 3. Then the 1 over 81 jumps across the equal sign, so 1 over 81 equals, and we jump that negative 4 across, so log base 3 of 1 over 81 is equal to a negative 4. Okay, now going in the other direction, writing a logarithmic expression in exponential form. I've got log base 7 of 343 is equal to 3. So remember, before, the base of the exponent became the base of the log. So now the base of our log is going to be the base of an exponent. The 3 is going to jump across the equal sign and become the exponent, equals, and our 343 is going to go the other way. So we've got 343. Okay? All right, this next one, log base 10 of 0.0001 is equal to negative 4. So again, the base of the log is now the base of the exponent. The negative 4 jumps across and is now the exponent on that 10. And the 0.001 is on the other side of the equal sign. Okay. Now it is important to note that the log of a negative number is not a real number. So if we got a problem that says we're taking the log of a negative, what that would mean is that it's a no solution or no real solution. All right, now some properties of logs. First one is the equality of exponents. Just says if b is greater than 0 and b is not equal to 1, if b to the u equals b to the v, then u equals v. So what that means is if they have the same base, then the exponents have to be the same. 3 to the x equals 3 to the 4th, so x has to equal 4 because they were both bases of 3. Here I have 5 to the 3x equals 5 to the 6, which means 3x equals 6. So when you would solve for x by dividing by 3, and you would get that x equals 2. All right. Now in order to evaluate a logarithm, and this is by hand, evaluating these logarithms, we've got 4 steps. First, you write it as an equation. In other words, put it into exponential form. Write with equivalent bases, and then solve for x using the equality of exponents property. So here I have log base 2 of 8. So I'm just going to say that equals x. That's writing as an equation. Now we write that in exponential form. So 2 to the x equals 8. Then you kind of have to think, okay, what 2 to what power would equal 8? Well, I know that 2 cubed is 8. So I've got 2 to the x equals 2 cubed. They both have bases of 2. So what I generally do is just mark out those bases, and I've got that x equals 3. Okay. All right, this next one, log base 3 of 1/9. So again, I'm going to say that equals x. And then 3 to the x equals 1/9. Now I need to write it with equivalent bases. So what I'm going to say is 3 to the x. And I know 1/9 is 9 to the negative 1. So I could say 3 to the negative 2 is equal to 1/9. You see that? How 3 to the negative 2 is the same thing as 1/9. So 3 to the negative 2 is 1 over 3 squared, which is 1/9. Okay. Now I have same bases, so I can mark them out. So x equals negative 2. All right, I'd like y'all to take a moment and do this next one. Log base 4 of 64. All right, I'm not going to work through it. Y'all can check Blackboard to see what the answer is. But you're doing log base 4 of 64. Okay, now going the other direction, solving a logarithmic equation. Here I have log base 4 of x is equal to negative 2. We're going to solve that for x. Now there's 2 steps on these. First, you're going to write it in exponential form. And then you solve for x. Okay, so log base 4 of x is equal to negative 2. So we need to write that in exponential form. So my 4 is now the base of the exponent. The negative 2 is the exponent, and that equals x. So 1 over 4 squared equals x. So 1/16 is x. Okay, I'm going to do another one. I've got a log base 6 of x is equal to 2. So exponential form would be 6 squared equals x, and 6 squared is 36. So x equals 36. All right, here's one for y'all to do. Log base 2 of x is equal to negative 4. Okay, again, you can check the filled in notes on Blackboard to get that one. Okay, I've got a couple of definitions here for you. A common logarithm is a logarithm with a base of 10. So if you ever see that it just says log of, let's say, 100, that means log base 10 of 100. And we've got the natural logarithm, which is a log with a base of e. And what we do on that is we just show it's the letters ln for natural log. That is the same thing as log base e. So we're going to solve a logarithmic equation containing a natural or common logarithm. Natural log of x is equal to negative 1. So remember that natural log is the same thing as log base e. So when I go to write that in exponential form, I'd say e to the negative 1 equals x, which is 1 over e. And just like I told y'all on Tuesday, anytime you've got an e, that's when you're going to have to use the calculator. So you'd have to plug that in, 1 divided by e, and you'd have x is equal to 0.37. Okay, log base x, log x is equal to 1.5. So remember, if there's no base, that means it has a base of 10. So this is 10 to the 1.5 equals x. And again, I would probably, because of the fraction or the decimal there, I would use the calculator. And you get x is equal to 31.6. Okay. All right, so our next topic here is the properties of logarithms. We've got a couple of properties you need to be aware of. First is the product property. Just says log base b of x times y is equal to log base b of x plus log base b of y. And this comes from the exponent rule of multiplying, where you're going to add the exponents. Same thing's happening here. So it's if you're multiplying, you're taking the log of something you're multiplying, you can separate them out by addition. Here's just some pictures that we can look at here, nothing really to write. Log base 7 of 9z is log base 7 of 9 plus log base 7 of z. Notice on the second one, log of x minus 2 times x plus 3, they've just split up those two factors. So log of x minus 2 plus log of x plus 3. And of course, it works with natural log as well. The quotient property, if you'll remember in exponents, when you're dividing, you're going to subtract the exponent. So here, if you're taking the log of a quotient, so something that you're dividing, you're going to expand it by subtraction. And again, here's some things. Log base 3 of y over 11. That's log base 3 of y minus log base 3 of 11. And we've got log of x plus 1 over x minus 1 is log of x plus 1 minus log of x minus 1. And natural log of 14 over w is the natural log of 14 minus the natural log of w. Okay, we've got the power property of logarithms. For any positive real numbers x and b, b is not equal to 1. And for any real number r, the log base b of x to the r is equal to r log base b of x. So you can take that exponent and you move it to the front. If you look at these examples, log base 4 of x to the 5th is 5 log base 4 of x. So that 5, that exponent, just moved to the front is what happened there. Okay? 2x minus 1 is the exponent, so that whole term moved to the front. Natural log of the square root of x, well, using our rational exponents, log base x, log of x to the 1/2, that 1/2 comes to the front, so 1/2 natural log of x. All right, so we're going to expand some of these. So I've got natural log of, I've got log base b of x squared times the square root of y. Okay, that is two separate terms there. This is a product. So to expand it, we would say log base b of x squared plus log base b of the square root of y. But we're not done. We've only used one property so far. I would probably just go in order. Do we have any quotients? Doesn't look like it. But we do have a couple of powers. So I'm going to take my 2 from the x squared and move it to the front. So I've got 2 log base b of x. And this square root of y, well, that's the same thing as y to the 1/2. So I'm going to take that 1/2 and move it to the front. Plus 1/2 log base b of y. Okay. I'm going to do another one. Natural log of x over yz squared. All right, so I'm going to say that that's going to be equal to natural log of x. Because it's divided, I'm going to say minus the natural log of yz squared. Okay, that's just one step. We're not done. Equals natural log of x. Now here we've got a product, so I'm going to say natural log of y minus the plus the natural log of z squared. And I did plus in there because it was just separating out that product. So I did put it in parentheses, which kind of shows me that I'm not quite done because parentheses won't be in our final answer. I'm going to distribute this negative, and I'm going to go ahead and grab this 2 right here and move it to the front of the natural log. So I've got natural log of x minus natural log of y. When I distribute that, it becomes a minus 2 natural log of z. Okay, I'm going to do one more. I'm going to leave the other 3 for y'all to do. I've got log 8 of the square root of x cubed y. So that's log base 8. Let's see. If I were to rewrite this as x cubed y to the 1/2, that 1/2 comes to the front. So far, with just one step, I've got 1/2 log of 8 x cubed y. Now I'm going to spread out the x cubed y by addition. So 1/2 log 8 x cubed plus log 8y. Now because that's just from that one log there, I do want to put parentheses there just to show that they're just a single term. I am going to go ahead and, let's see, at this point, I'm going to move this 3 to the front of just that log. So 1/2 3 log 8 of x plus log 8 of y. And finally, to get all the way finished, we're going to distribute the 1/2, which leaves me with 3/2 log base 8 of x plus 1/2, because there's not a coefficient on that one, log base 8 of y. Okay, kind of a way to check on these. If you've got one that started, if it's in a product, then it's just a single level. That means that both of your terms in the end will be positive. Like on B there, where we have 1 up top and 2 in the denominator, notice that in my answer, the x, which was up top, is positive, the y is negative, and the z is a negative. So anything that started in the bottom of a fraction will be negative when you expand it. Okay? You can't have any exponents in expanded form, so make sure you move them all to the front. Yeah, I think those are all little tricks I can think of for that. I have left 3 here for y'all to do. I've got log base b of x squared over y, and natural log of y to the 1/3 z cubed, and log base 8 of the cube root of xy squared. Okay? Okay. Writing logarithmic expressions as a single logarithm. So this time I'm going the other way. Instead of expanding it, we're going to compress it all together into just one term, or condense it, I believe is the phrase we use. I've got 3 log base 5 of x plus log base 5 of y minus 2 log base 5 of z. So the first thing you're going to do is check for any coefficient, because they are going to be moved to the exponent of those terms. So here I have log base 5 of x cubed plus log base 5 of y minus log base 5 of z squared. Okay, next what I'll do is condense any that I can. And they all have same bases, so the 2 positive ones are going to be together as a product. So log base 5 of x cubed y, and then the minus the z squared there is going to move to the denominator. So there we have it. Log base 5 of x cubed y over z squared. Okay. All right, so this next one I have is 2 times log base 4 of x plus 3 log base 4 of y minus 2 log base 4 of z. So just starting inside the parentheses, kind of using PEMDAS basically here. I'm going to take my 3, make it the exponent on the y, take the 2, make it the exponent on the z. So I've got 2 log base 4 of x plus log base 4 of y cubed minus log base 4 of z squared. Then continuing to work inside the parentheses, I could have log base 4 of x y cubed over z squared and then finally I'm going to take my 2 and move it. So I've got log base 4 of x y cubed over z squared squared. Kind of need to write that one again. Log base 4 xy cubed over z squared squared. Okay? And that would be the answer on that one. I'll do one more. I've got 1/3 times 2 natural log of x minus natural log of y. So I'd start by taking the 2 and moving it to that exponent place. So I've got 1/3 natural log of x squared minus natural log of y. Staying inside the parentheses, I still have my 1/3. I can put these together. The x squared will be on top in the numerator, and the y goes to the denominator. Take that 1/3 and put it as the exponent. So we've got natural log x squared over y to the 1/3, which is probably as far as you'll need to go on that, but they might require that you change it to the natural log of the cube root of x squared over y. Okay. So I left 3 there for you. I've got 2 log base b of x minus 3 log base b of y minus log base b of z. 3 log base 5 of x minus log base 5 of y plus 4 log base 5 of z. And 1/2 2 natural log of x minus 5 natural log of y. So you can practice those on your own and just check the Blackboard notes to see what the answers are. Okay, some other properties of logarithms. We've got the logarithmic property of 1, which says right here that the log base b of 1 is equal to 0. So anytime you're taking the log and it's 1 that you're taking the log of, you're going to get 0. So those 3 examples are showing you how that works. The inverse property of logs just says like log base b of b to the x is equal to x, which tells you that b to the log base b of x is equal to x. That's actually a process called exponentiating that we use in solving. But if you have same bases, like you look at number 1 here, log base 5 of 5 to the x, well, that cancels. Log base 5 of 5 just brings down the x. Okay? And then the 1-to-1 property for any positive real numbers x, y, and b, if log base b of x is equal to log base b of y, so if the bases are the same, then basically you can mark them out and x equals y. Okay. And we've got the change of base formula. Now, you know about the common log. There, a long time ago, when you didn't have calculators where you could write in your own base or change your base, you had to do everything in the common log. And so this just shows you how to change things to the common log. So here I have log base 7 of 32. So to change that to a common log, what we're going to do, just using this formula, basically what we have here, the b is what you want your new base to be. So we're going to say b is equal to 10. A is your old base, so the one they gave you. So in this case, it was 7. And of course, n in our problem is 32. It's just the number, okay? So I've got log base 7 of 32 is equal to log 10 of 32 over log 10 of 7. So you'd evaluate that in the calculator, which I can show y'all tomorrow how to do that. But yeah, you would just put that into your calculator. In this case, you would get 1.7810. Okay, this next one, log base 4 of 2.4. You know what, I'm going to leave that one. Let's do the next one. B's not hard, but I only wanted to do one more of these examples, so I want to do letter C. We've got f of x is equal to negative 3 log base 7 of 2x minus 5. So what we're going to have to do here is to use our common log is, I'm trying to see what this says. Hold on. Yes, okay. So I'm going to say it's negative 3, just kind of hanging out front. And we're wanting to get this in terms of natural log. So that's going to be our LN, natural log. So times natural log of 2x minus 5 over natural log of 7. So on this one, our desired base was E. So the B was E is what we were doing, okay? So that's where that's coming from because it's just log base E. So that's why it's natural log of 2x minus 5 over natural log of 7. And again, you would just put that into the calculator. It is saying that you just keep it in terms of natural log, so we could leave it just like that. Okay. Here, I kind of fumbled on that one, so let's do this one as well. Rewrite f of x is equal to 4 log 8 of 3x plus 4 in terms of the common log. So because it's the common log, that's like what we had before. Our b would be equal to 10. So I'm going to say 4 times the log of 3x minus 5. And it does have a base of 10, but we don't have to write that, over log of 8. So that would be our answer right there.